Welcome back to Psych 1303. My name is Nicholas Evans, and in today's lecture and the next one, we're going to be talking about null hypothesis significance testing and the t-test. But before we begin, I'll review the main points from the last lecture. During the last lecture, we clarified the distinction between sample statistics, population parameters, and characteristics of the sampling distribution. Sample statistics describe the characteristics of a particular sample. Population parameters describe the characteristics of a population and are usually represented by Greek letters. The characteristics of a sampling distribution are just what the name implies. The main topic of the last lecture concerned the confidence interval of pi around p. This confidence interval is what pollsters need when they report their results. So, for instance, when Joanna P. pollster interviews 1,000 East Virginia voters and finds that 53% intend to vote for Christina Green, that tells her P equals 53%. But what she really wants to know is pi, the percentage of voters in the whole state who plan to vote for Green. If she constructs a 95% confidence interval around P, she can say, I am 95% confident that pi lies somewhere between 50% and 56%. During the first part of the last lecture, we explained what the confidence interval of pi around P tells us. For purposes of explanation, we began by making a confidence interval around P that was the same length as the confidence interval of P around pi. So, in this sampling distribution, the red line along the x-axis shows the confidence interval around pi, and the yellow yardstick above it is the new confidence interval that is the same length. We can place this new confidence interval so it is centered on 0.53. This confidence interval around 0.53 includes the red dot at 0.55, which represents pi. So, in other words, this confidence interval centered on the sample value of 0.53 includes the true value of pi in the population. Similarly, if we center the new confidence interval on 0.575, we see that 0.55, the true value in the population, falls within the confidence interval. However, if we center the confidence interval on 0.51, then the true population value of 0.55 does not fall in the confidence interval. And again, if we center the confidence interval on 0.59, then pi does not fall within the confidence interval. So, for some values of p, like 0.53 and 0.575, the portable confidence interval around them includes pi, the true population value. And for other values of p, like 0.51 and 0.59, the confidence interval around them does not include pi. So, you can see there's a pattern here. When p is within the confidence interval around pi, then pi is within the portable confidence interval around p. For instance, here p is about 0.595. We can see that pi, at the center of the red dot, is not included in the confidence interval for this value of p. But for smaller values of p, the end of the yardstick gets closer to the center of the red dot. And finally, there is a value of p when pi lies within the confidence interval of p. When that happens, the blue dot, representing p, lies within the confidence interval of pi. So, if pi is within the confidence interval around p, it is also true that p is within the confidence interval around pi. Now, as the pink rectangle on this graph shows, 95% of the samples have a value of p between 0.52 and 0.58. That is, 95% of the samples have a value of p that falls within the confidence interval around pi. For these samples, pi falls within the 95% confidence interval around p. This is the logic that justifies Joanna P. Polster and other pollsters calculating a confidence interval for p around pi. So, let's say Joanna randomly draws a sample of voters and calculates p, and she finds that it is 0.53. She can construct a confidence interval around 0.53 that is the same length as the confidence interval around pi. There is a 95% probability then that pi will be in this confidence interval around p. So, Joanna can say that she is 95% confident that pi, the number of voters in the whole state who intend to vote for green, lies between 50% and 56%. Now, in the last lecture, you also learned how to calculate the confidence interval for pi around p. Here are the formulas for the upper and lower limits of the confidence interval. You start with p, the proportion in the sample, and then you just find the numbers that are 2 standard errors above p and 2 standard errors below p. There's a bit of a problem, however, because you don't know the standard error of p around pi. You could calculate the standard error if you knew sigma or pi, which are population parameters. However, you don't know those either. So, what statisticians do is substitute estimators for parameters. So, estimators wear these little hats. So, for instance, the estimator for pi is pi with a little hat, and the value of this estimator is p, the sample proportion. So, the idea here is when you need pi, the population proportion, in a formula, you substitute p, the sample proportion. So, if we start out with equations like these that contain population parameters that we don't know, we can substitute the estimators for the parameters. So as you can see, the estimator sigma hat is substituted for the parameter sigma, and the estimator pi hat is substituted for the parameter pi. And then we can plug in the estimator values in the formula in place of the estimators. So for instance, in this formula, we substitute p, the sample proportion for pi. We know that p for Joanna P. Polster is 0.53, so all we have to do is plug that in. And when we do the math, we find that the estimated value of sigma is 0.499. So all we have to do then is plug this value into the formula for the standard error, and we get this. We also know that the sample size is 1,000, and when we plug that in and do the math, we get 0.0158 as the value for the standard error. We then take that value and plug it in to the formulas for the confidence interval, and then all we have to do is do the math. And finally, in the last lecture, there was a brief example of how to calculate the confidence interval for mu around the sample mean. For instance, suppose you had a random sample of 5th grade girls and you calculated the mean height in this example as 52 inches. You might want to calculate a confidence interval around this value to identify the likely values of mu, the mean height of the whole population of 5th grade girls. The calculation of the confidence interval is basically the same idea as what you already know for p and pi. Here are the formulas for the confidence interval, and as you can see, they are the same as the formulas for p and pi, except that you substitute the mean of x for p. And again, you can see that there's a problem that you don't really know the standard error. But again, statisticians just substitute estimators for parameters. So here's the familiar formula for the standard error, but substituting the estimated value of sigma for sigma. For the estimated value of sigma, you can just substitute the sample standard deviation, then you plug in the numbers and calculate the standard error. After you calculate the standard error, then all you have to do is plug this value into the formulas for the confidence interval. So we did this with an example involving bags of cookies and found that the confidence interval for mu was 0.44, 0.46. That is, we can be 95% confident that mu, the number of cookies per bag in the population, is between these two numbers. The manufacturer's claim that there are an average of 50 cookies per bag does not seem likely to be true. So, after covering the material that we discussed last lecture, we are now ready to go on to today's topics. To begin with, I'll talk briefly about the sampling distributions of statistics other than p and the sample mean. Now, remember how the sampling distribution of p was created. We started with a population. We drew a very large number of samples from this population. Each sample included the same number of individuals, and in each sample we calculated p, and we made a long list of these values of p, one value for each sample. Finally, we created a histogram of all these values of p, and we had the sampling distribution of p. We can create a sampling distribution for any sample statistic by following the same process. So, for instance, we can create a sampling distribution for the standard deviation. We draw a very large number of samples with the same number of individuals in each sample. In each sample, we calculate the standard deviation until we had a very long list of standard deviations, one for each sample. And then we create a histogram which represents the sampling distribution of the standard deviation. However, the sampling distributions for the standard deviation and other statistics are not always like the sampling distributions for p and the sample mean. For instance, the sampling distributions of p and the sample mean are normal if n is greater than 30. How do we know that? It has actually been proven by the central limit theorem. Now, let's talk about the sampling distributions of statistics other than p and the sample mean. The sampling distribution for these other characteristics is not necessarily normal. The central limit theorem generally does not apply to them. It applies only to the sample mean and p. Actually, we could say that the central limit theorem only applies to the mean, because p is a mean, as we have learned when we were talking about Bernoulli variables. For instance, let's consider the variance of a sample. What is another name for the variance? If you recall, the variance of a sample is also called the mean square, and it's equal to the square of the standard deviation. Now, we can create a sampling distribution of the variance by drawing a large number of samples, calculating the variance for each one until we have a very long list of numbers, and then simply plotting these numbers as a histogram. This sampling distribution would not be normal. So here is the sampling distribution of the variance when sample size is 6. As you can see, this distribution is not normal in shape. So thinking back to when we discussed shapes of distributions, would you say it is positively skewed or negatively skewed? If you said it's positively skewed, you would be correct, because you can see that the tail points to the right in the positive direction. Now, a distribution with this shape has a name. This is called the chi-square distribution with 5 degrees of freedom. The df labeled at the bottom stands for degrees of freedom. So if you go on to take an advanced statistics course, you will study an important statistical procedure called ANOVA, which is short for analysis of variance. As the name indicates, analysis of variance deals with variances with sampling distributions of the variance, which are chi-square distributions. But we won't be dealing with ANOVA or chi-square distributions in this course. So let's use another example of a sampling distribution that is not normal. The sampling distribution of R, or the correlation coefficient. Suppose you have two variables, height and weight. You can draw a very large number of samples, each with the same number of individuals. You measure height and weight in each sample, and then you calculate R, the correlation between height and weight in each sample. You will then end up with a very long list of values of R, one value for each sample. And then you can use these values to create a histogram of the sampling distribution. Here is the sampling distribution of R when rho equals 0.90. Rho is the name for the population parameter. It is the correlation between height and weight in the entire population. Because it's a population parameter, it is written as a Greek letter, rho. When it's written down, rho looks like our letter P, as you can see on this slide. But it is actually the Greek letter for R, and has the same sound as R. Now, the distribution shown in this slide is the sampling distribution of the sample correlation, R, when rho, the population correlation, is 0.90. As you can see, the sampling distribution is not normal. The reason is that the correlation is close to 1. But as you remember, the correlation can't be larger than 1. So the sampling distribution can't be normal on the right side. It can't have a long tail extending on the right side the way it has a long tail on the left side. So when rho, the true population correlation, is close to 1, the sampling distribution of R is asymmetric, as you see here. So, as these examples show, the sampling distributions for some other statistics are different from the sampling distributions for P and the mean. Some of these other sampling distributions do not have a normal shape. And here's another difference. In the sampling distributions of P and mu, the expected value of P is equal to pi, and the expected value of x bar is equal to mu. That is, the average of the sampling distribution is equal to the average in the population distribution. But the sampling distributions of other statistics can be different. That is, for some statistics, the expected value of the sampling distribution is not necessarily the same as the population parameter. For instance, here's the sampling distribution of R I showed you earlier. Now, as you recall, rho equals 0.90. That is, the correlation of the two variables in the population is 0.90. But the expected value of R in the sampling distribution is not equal to 0.90. Here is the expected value of R. Because the distribution is negatively skewed with a long tail to the left, the average of the distribution, that is, its expected value, is pulled to the left away from 0.90. Now let's talk about the sampling distribution of the sample standard deviation. Now I described earlier how to create the sampling distribution by drawing a very large number of samples and calculating the standard deviation in each. Now, it so happens that the sampling distribution of the standard deviation is normal if n is greater than 30. So it's like P and the sample mean, which also have normal sampling distributions when sample size is greater than 30. However, with the sampling distribution of SD, the expected value of the standard deviation is not equal to sigma, the standard deviation in the population. Specifically, the expected value of SD is always less than sigma, the population standard deviation. Another way of putting it is the sample standard deviation is a little too small. For instance, suppose you select a sample of 100 children and measure their height. You find that SD, the standard deviation of height in the sample, is 2 inches. In this case, sigma, the standard deviation of height in the entire population of children, is probably a little more than 2 inches. So we say that SD in the sample slightly underestimates sigma in the population. Usually, SD in the sample only slightly underestimates sigma in the population, and it's really nothing to be concerned about. However, statisticians like to be precise, so they have developed a correction for estimating sigma. Remember, the estimator for sigma has a little hat on it. When you want to calculate the estimated value for sigma, statisticians have shown that you get the most accurate results with a correction, and here it is. When you are calculating the standard deviation in a sample, calculate SD just like you always do, but At the step when you are calculating the mean square from the sum of squares, divide by n minus 1 rather than by n as you usually do. I'll show you what this means. First, let's review the way that the standard deviation is usually calculated. After you have calculated the standard deviations of the scores from the mean and square the deviations, you sum up the squared deviations to get the sum of squares, or SS. Then you divide the sum of squares by n, the number of scores, and this gives you the mean square, which is also called the variance. And finally, you calculate the square root of the mean square, and this gives you the standard deviation, or SD. But suppose you want to calculate the estimator of sigma, shown here as sigma with a little hat. Remember, the SD slightly underestimates sigma. So, when you calculate the estimator for sigma, it includes a small correction to SD, and so here are the steps. You begin just the same way as before, that is, you calculate the deviations from the mean, square them, and then sum the square deviations to get the sum of squares. But the next step is a little different. Normally, you would divide by n to get the mean square, but instead, this time you divide by n minus 1. This gives you a number called s squared. S squared is usually very close to the mean square. In fact, some books call it the mean square. The third step is the same one you know for the standard deviation. You just take the square root. In this case, you are taking the square root of s squared. The result is called the estimated value of sigma, with the little hat, or some books call it s. S is usually just a little bit larger than SD, calculated the usual way. In step 2, we divided by n minus 1. N minus 1 is called the degrees of freedom, or DF for short. When you learn about ANOVA in the advanced statistics class, you'll see n minus 1 a lot. And you can remember it's called the degrees of freedom, and it is used as a correction factor. You will also see n minus 1 in other formulas, and again, you can think of it as basically being the sample size with the slight correction factor. So it's possible to construct a sampling distribution of S. All you would have to do is follow the normal procedure. Draw very many samples, calculate S in each sample until you have many values of S, and then use them to construct a histogram that shows the sampling distribution. The expected value of S in the sampling distribution is equal to sigma, the standard deviation of the variable in the population. Statisticians say that S is an unbiased estimator of sigma. That is, S does not tend to systematically underestimate sigma. The average value of S, that is, its expected value, is sigma. Now that you understand the best way to calculate the estimator of sigma, let me tell you how to calculate it for this course. For instance, when you are trying to calculate the standard error of the mean, you will want to calculate this estimator. When you do, don't use the correction. That is, when you calculate the estimator of sigma, just do the calculations for the SD the way you always have in this class until today. That is, after you calculate the sum of squares, just divide by n as you always have to get the mean square, and then calculate the square root of the MS just as you always have to get the standard deviation. For this course, plug in SD, not S, when you need the estimator for sigma. I am asking you not to make the correction and not to use S, because when you're beginning to learn statistics, it's important to focus on the main ideas and not get distracted by fine points or picky details. And the correction factor for the estimator of sigma is a fine point that you shouldn't be worrying about now. I'm only telling you about it so you won't get surprised when you run into it when you take advanced stats. When you get to the advanced stats, you can calculate the estimator of sigma using S. That is, you can divide the sum of squares by n minus 1, which is the correction, and you can calculate the square root from that. Your textbook in advanced stats and your instructor will indicate if they want you to do this, but for the time being, as I say, do not use this correction. Now we're ready for the main topic that we'll be focusing on during the rest of today's lecture, and all of the next lecture: null hypothesis significance testing and the t-test. The abbreviation for null hypothesis significance testing is NHST. The t-test is designed for use in two-group studies, so let's discuss what a two-group study is. In a two-group study, the research is comparing the means of two groups on a dependent variable. Here's an example. Suppose a researcher selects two samples or groups of students at Colbert University. One of the samples consists of 100 men and the other sample consists of 100 women. The researcher gives IQ tests to all the students, then calculates the mean IQ score in each group and compares these means. In statistical terms, we say that this study uses a two-group design and that the dependent variable is IQ scores. As you can see, the researcher has found a difference between the groups in regards to IQ scores. The mean IQ for the women is 106, whereas the mean IQ for the men is a bit lower, 104. Now, the researcher faces a very serious question. Did the women score better than the men by chance? Now, there's another way we can put this question. Did the women score better than the men due to sampling error? After all, as we learned while studying polls and surveys, sample means usually differ from the population mean. This is what we call sampling error. Is it possible the two populations have the same mean? That is, even though these two samples have means that are slightly different, is it possible that in the entire population there is no difference? Here are the populations of all the men and women at Colbert University. Maybe the mean IQ in the population of all women is 105, which is the same as the mean IQ in the population of all men. The question marks indicate that we don't know for sure what the true situation is in these populations. But it's possible that the mean IQs in the two populations are equal. Maybe the mean IQ is 105 for both men and women. It's true that the sample means are different, with 106 for women and 104 for men, but maybe that's just sampling error. Now, so far we just have maybes, but we can be a little more precise if we actually think about it. So let's start with the question. What is the standard error of the mean in the researcher sample of Colbert men? We already know that the standard deviation in the sample is 15 and the sample size n is 100. We can use these numbers to estimate the standard error of the mean. What is the standard error of the mean in the sample? Well, in the sample, the standard deviation is 15 and the sample size is 100. So that's enough information to calculate the standard error. Here's our general formula for the standard error of the mean. The standard error of the mean is equal to sigma divided by the square root of n. We don't know sigma, so we will use an estimator of sigma. So here's the same formula again, but we substitute SD, the sample standard deviation, for the estimator of sigma. Then we just plug in the numbers. SD is 15, n is 100. 15 divided by the square root of 100 is 15, divided by 10, which is 1.5. So the standard error of the mean is 1.5. So now that we know the standard error, let's ask another question. What is the confidence interval of mu around the sample mean and the sample of men? We already have the numbers we need to construct the confidence interval. We know the sample mean is 104, so that's at the center of the confidence interval. And we just calculated the standard error of the mean, and it's 1.5. So with these numbers, we can calculate the confidence interval. The upper limit of the confidence interval is the mean plus 2 standard errors, and the lower limit is the mean minus 2 standard errors. The standard error is 1.5. So the upper limit is the mean plus 3, and the lower limit is the mean minus 3. Now, here's a graph that shows the sample means for the men and women at Colbert University. The dot on the left is the sample mean for the men, 104. The dot on the right is the sample mean for the women, 106. Now, let's draw the 95% confidence interval around the dot on the left, the sample mean for the men. The confidence interval extends from 101, which is the mean minus 3, to 107, which is the mean plus 3. We can be 95% confident that mu, the population mean for the men, lies somewhere on this confidence interval. Could mu be 105? Yes, 105 is on the confidence interval, so mu, the population mean for men, could be 105. In fact, 105 is pretty close to 104 and stands a pretty good chance of being equal to the population mean. Next, the sample mean for women is 106, so let's draw a 95% confidence interval around it too. The standard deviation and sample size are the same for the women as for the men, so the standard errors will also be the same. So here's the confidence interval around the mean for women. This blue confidence interval extends from 103, which is 106 minus 3, to 109, which is 106 plus 3. For the women, we can be 95% confident that mu lies somewhere between 103 and 109. Could it be that mu, the population mean for women, is equal to 105? Yes, 105 could easily be the population mean for the woman. And here's 105. And we can see by looking at the two confidence intervals that the population mean for men could be equal to 105, and so could the population mean for women. So what have we learned from this? It's true the samples of 100 men and 100 women have different means on the dependent variable. But it's entirely possible that there is no real difference in the population of all men and women at the university. The 2-point difference between sample means could be due to chance, or, to be more specific, the difference between the sample means could be due to sampling error, or to put it a third way, the difference may not indicate a real difference between the populations. Or, to put it a fourth way, the difference between the sample means is not statistically significant. These are just 4 ways of saying the same thing, using different words and different levels of specificity. So let's try another example. This is another 2-group study. This time, one sample consists of students with a 2.0 grade point average, or GPA, and the other sample consists of students with a 4.0 GPA. There are 100 students in each sample, and again, the dependent variable is IQ scores. This graph shows that the students with a 2.0 GPA have a mean IQ of 100, and the students with a 4.0 GPA have a mean IQ of 110. That's a 10-point IQ gap between the two samples. But is it possible that the two populations have the same mean? That is, if we got all the 2.0 students at Colbert and all the 4.0 students, not just these samples, is it possible these two populations would have the same mean? The two samples each have a standard deviation of 15 and a sample size of 100. So the standard error for each sample is the same as for the samples of men and women we just discussed. Here are the means of the two groups. On the left are the 2.0 students with a mean IQ of 100. On the right are the 4.0 students with a mean IQ of 110. And here are the confidence intervals around each of the means. Now, is it likely the 2.0 students have the same population mean as the 4.0 students? The confidence interval on the left indicates that mu in the population of 2.0 students is probably 103 or lower. The confidence interval on the right side indicates that mu in the population of 4.0 students is probably 107 or higher. There's no overlap between the two confidence intervals. So in this case, the difference between the two sample means is 10 points. This 10-point difference is just too big to be explained by sampling error. There is probably a real difference between the populations. The 10-point difference between sample means is probably not due to chance, or to be a little more specific, the difference between sample means is probably not due to sampling error, or to put it a third way, the difference between sample means probably indicates a real difference between the populations. Finally, to put it a fourth way, the difference between the sample means is statistically significant. These are just 4 ways of saying the same thing. So this is a problem that researchers constantly face. In a 2-group study, there's always a difference between the sample means. It would be a miracle if 2 samples with 100 individuals in each sample had exactly the same means. I have never seen such a thing happen before. So there's always a difference, no matter how tiny, between the means of the 2 groups. So how do the researchers decide if this difference in sample means is statistically significant? That is, how do researchers decide whether this difference between sample means is simply due to sampling error, or whether instead it indicates a real difference between the underlying populations? The way that researchers usually deal with this problem is called null hypothesis significance testing, or NHST for short. To understand null hypothesis significance testing, though, you first need to understand a new sampling distribution. It's called the sampling distribution of the difference between 2 sample means when the null hypothesis is true. Now, this is a very long name, so we will shorten it a bit by using some symbols and abbreviations. First, we'll shorten this phrase, the difference between 2 sample means. Down at the bottom of the slide, you can see the abbreviation, the short mathematical way of saying the same thing. We have 2 samples. The mean of the first sample is called sample mean 1, and the mean of the second sample is called sample mean 2. The difference between them is sample mean 1 minus sample mean 2. So we'll substitute the abbreviation like this. Next, we'll shorten this phrase, the null hypothesis is true. Down at the bottom of the slide, you can see the abbreviation, the short mathematical way of saying the same thing. We have 2 populations. The mean of the first population is called mu1, and the mean of the second population is called mu2. The null hypothesis is that mu1 equals mu2. The null hypothesis can be written in a different form, as shown here. Mu1 minus mu2 equals 0. These 2 forms of the null hypothesis are equivalent to each other. That is, if mu1 equals mu2, then we can prove with a little algebra that mu1 minus mu2 equals 0, and vice versa. If mu1 minus mu2 equals 0, we can prove that mu1 equals mu2. So these mathematical expressions are equivalent. Sometimes statisticians use one form, sometimes they'll use the other. For the present purposes, we'll use the form mu1 minus mu2 equals 0, and we'll substitute it into the name. So now our slide says the same thing as it did before, but using mathematical abbreviations. So this is what I'm about to teach you, the sampling distribution of the difference between 2 means when the null hypothesis is true. Let's begin by very quickly reviewing how to construct the sampling distribution of P, or the sample mean. There are 5 steps. First, you begin with a large population. Second, you collect a very large number of samples from the population, abbreviated with K. Actually, you're supposed to collect an infinite number of samples, but we'll just say very large. Third, each sample must include the same number, or n, of individuals. Fourth, calculate P for each sample. So you end up with a very long list of P's, one for each of the K samples. And fifth, you plot P from the samples as a histogram. This histogram shows the sampling distribution. The steps for constructing the sampling distribution of the difference between 2 means are very similar, but there are some differences. So here are the 6 steps for constructing the sampling distribution for this difference. First, you begin with 2 populations, like males and females, or students with 2.0 GPA and students with 4.0 GPAs. I'll call these 2 populations population 1 and population 2. Second, you assume that the population means are the same. To use mathematical language, you assume that the mean of the first population, written as mu with the subscript 1, is equal to the mean of the second population, written as mu with the subscript 2. Or, as I said earlier, there is a second form of this assumption, that the mean of the first population minus the mean of the second population is 0. These 2 forms of the assumption are mathematically equivalent. This assumption that the two population means are equal is called the null hypothesis. The symbol for the null hypothesis is a capital letter H with a zero subscript. It's called the null hypothesis because null means zero or nothing. So the null hypothesis is a hypothesis that there's nothing there, that there is no difference between the population means. The third step is to collect a large number of paired samples. A paired sample consists of one sample from the first population and one sample from the second population. For instance, you might collect one sample of 100 individuals from the first population and another sample of 100 individuals from the second population. Together, these two samples form one paired sample. Fourth, each paired sample contains a sample of n individuals from population 1 and another sample of n individuals from population 2. We'll call these sample 1 and sample 2. For instance, if n is 100, then sample 1 in each paired sample consists of 100 individuals, and sample 2 also consists of 100 individuals. So the number of individuals in each paired sample is 200. Fifth, for each paired sample, calculate the mean of sample 1 minus the mean of sample 2. As you can see in this slide, the mean of sample 1 is represented by the symbol for the mean with a little subscript 1, and the mean for sample 2 is represented by the symbol for the mean, but with a little subscript 2. So this data sheet shows you the numbers that are involved. It shows data from 10,000 paired samples, that is k equals 10,000, but because it would take a long time to show you the data from all 10,000 samples, the slide shows the data from only the first few samples and the last few samples. The dots in the middle indicate that I have left the middle samples out of the slide. Let's take a look at the slide from the first paired sample. So we can see that n is 100. That means that sample 1 includes 100 individuals, and sample 2 also includes 100 individuals. So there are 200 individuals in the paired sample. The mean for sample 1 is 106.15. The mean for sample 2 is 104.16. If we subtract the second mean from the first mean, we get this number, that is 106.15 minus 104.60 equals 1.55. This number, 1.55, is the difference between the two sample means. When we're done with the first paired sample, we do the same thing with the second paired sample. That is, we calculate the means of sample 1 and sample 2, and then we subtract the two means. This time the difference between the two sample means is 0.24. And then we keep it up, doing the same thing again and again for all 10,000 paired samples. And in the right-hand column, we end up with the difference between the two means for 10,000 samples. So there are 10,000 numbers in this column, though I can't show them all to you here. These 10,000 numbers are what we want and what we're now going to use in the sixth and final step. The sixth step is to make a histogram using the 10,000 numbers that we just calculated, the 10,000 values for the differences between the two means. And this histogram is a sampling distribution of the difference between the two sample means when the null hypothesis is true. Next, I want to call your attention to three important features of this sampling distribution. Let's start with the expected value of the sampling distribution. So here is the sampling distribution. What do you think the expected value is? As you can see, the sampling distribution is symmetric. So the mean, that is expected value, is right at the center here. So the expected value is 0. As you remember, we started by assuming that the null hypothesis is true. That is, we assume that the two population means are equal, and that the difference between the two population means is therefore 0. Mu1 minus mu2 equals 0. If the difference between the population means is 0, it can be proven mathematically that the expected value of the difference between the sample means is also 0. That is, if the null hypothesis is true, the expected value of the difference between the sample means is 0. The second characteristic of the sampling distribution that I want to call to your attention is its shape. What do you notice about the shape of the sampling distribution? Well, as you can see, it's normal. The sampling distribution of the difference between two means is normal if n is 30 or greater. As you remember, this was also true regarding the sampling distribution of p and the sampling distribution of the mean. So it's the central limit theorem at work again. The third thing I'd like you to notice is that some values of the difference between the means are common, others are uncommon. Values close to 0 are common. On the other hand, values far from 0 are uncommon. The sampling distribution, as you can see, is normal, and its average, its expected value, is 0. So, as we would expect, most values of the difference between the two means are in the middle and near 0. On the other hand, values far from 0 are uncommon. So put another way, we expect that the means of sample 1 and sample 2 will usually be close to each other, so that the difference between them is small and close to 0. On the other hand, we don't expect that the means of the two samples will be far apart or that the difference between them will be large. We have covered a lot of ground today. You now have the background information you will need to understand null hypothesis significance testing as well as the t-test. This is the topic we will cover in the next class, but for now, we are going to call it a day. So I want to thank you for joining me, and remember to keep up on the reading and homework for Chapter 11, which covers the material we discussed today.